These notes are from section 6.2, Real Applications of Normal Distributions. So the goal for this section is to extend the concepts from the standard normal distribution to apply to distributions of any normal random variable x. So this is what we had for the standard normal distribution. We had that the mean was 0, and we used a variable z, or z-scores, along the x-axis. And so we had the standard deviation was 1, and we used the variable z. Now we want to look at other normal distributions where the mean is not 0, where the mean is something else, and where we're using the random variable x. And we want to see how we can standardize these contexts by converting them into contexts that look more like what we worked with in section 6.1. And we're going to do that by converting the x values into an equivalent z-score. So we've learned before how to find the z-score. We did it in the context of a unit where we were looking at sample statistics. And so the notation looked a little bit different because now we're talking about population parameters. Before it said x minus x bar divided by s for the formula. But here, since we're talking about population parameters, our formula is going to be x minus mu divided by sigma. So it's still the same z-score that we've worked with before. For instance, you might remember that when x is less than the mean, the z-score is going to be negative. When x is greater than the mean, the z-score is going to be positive. And that if x equals the mean, then the value of z is going to be 0. So the conversion that you're going to use is just this equation. And if you want to write that in here, you can. So this is going to be x minus mu over sigma. That's how we're going to be converting from a normal distribution in terms of the random variable x into a standard normal distribution. All right, so here's our first example. It says men have heights that are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. What proportion of men are taller than 72 inches? And when it says what proportion of men, they're saying essentially a synonym of what's the probability that a man randomly chosen would be taller than 72 inches. It's just another way of phrasing it. So when we look here, you can pretty easily in the context of these problems tell how x is being defined, but it's still good to write it out anyway. It's a good practice for when we get to more complicated problems or things where it might be a little bit more hidden or something we'd have to think through more. So the x here represents the heights of men in inches. And so what the problem is asking us to find is we want the probability that the height is greater than 72. So if I have the probability that x is greater than 72, I would love to use this chart that we learned about in section 6.1, but unfortunately I can't because 72 isn't even on this chart, and this chart is in terms of z-scores, which is a whole different variable. So what I need to do is I need to do this conversion and standardize this and rewrite this variable x in terms of z and the z-score so that I can use that standard normal distribution table to find the probability. So I'm going to find the z-score. I'm going to do my data point 72 minus the mean 68.6 divided by the standard deviation of 2.8. And with z-scores, we round to 2 decimal places. Easy to remember because when you use the chart, that's the only space that you're going to have. So I like to type this as a fraction, and on my calculator to get to the fraction, I use the green button, alpha, and then y equals, and it's the first option right there. 72 minus 68.6 over 2.8. Another way you can type that in and not have a computation error is if you type the top in parentheses and then divide by the bottom like that. You get the same answer. So the z-score is approximately 1.21. So that means that another way of saying this exact probability is to say the probability that z is greater than 1.21. We just converted it into a different variable, and that variable is the z-score. So now we remember when we work with this table that the table finds the area to the left, not the area to the right, as we can see in this picture. So I am going to use the z-score of 1.21, but I need to use the area to the left in my computation. So I'm going to find the complement, 1 minus the probability of z is less than 1.21, and so that's the whole area, that's 1 minus the probability of this side over here, and then I'll go ahead and calculate that. So 1 minus 1.21 would be 0.8869. And then I can go ahead and subtract. So if you were doing a problem like this, this is all the work I would expect to see if you're showing your work. The original probability statement, converting it into a z-score, the z-score that you're using as a probability statement, and then here the work where you're finding the complement, and then the final answer. This is good work to be showing that demonstrates your understanding of what you did and doesn't skip any steps. All right, let's look at the next example. So here it says, until recently, the U.S. Air Force required pilots have heights between 64 inches and 77 inches. Heights of women are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. What proportion of women meet the height requirement? So x, the variable x, represents the heights of women in inches, and what we are trying to find is the probability that women are between 64 and 77 inches tall. So we're not going to be able to find 64 and 77 on our standard normal distribution table, so we need to convert this into those z-scores. So we're going to have 64 minus 63.7 over 2.9, and 77 minus 63.7 over 2.9. So we're going to have 2 to calculate. So 0.10, 4.59. So what we're really looking for is the probability that the z-score is between 0.10 and 4.59. And so to find that probability, we always do the rightmost minus the leftmost, or the upper bound minus the lower bound. So the probability that z is less than 4.59 minus the probability that z is less than 0.10. Okay, and then this is an interesting one to do on the table because 4.59 is a pretty high z-score. So the z-scores go up to 3.8 They go up to 3.89 at 0.99999, and then they stop there. They don't go any further, but there is a note down here, and it says z-scores or z-values that are greater than 3.89, and this would qualify. 4.59 is greater than 3.89. They produce a probability of 1, and it's not that they actually hit 1, it's that the 0.9s are repetitive enough that it's approximating 1. Similarly to how we have, not on this table, but in that other table, binomial distributions, we had some probabilities that approximated 0. They were just, you had 3 decimal places, and when you cut off the 3 decimals, some of the numbers after that got cut off, and so you had 0.000, even though it didn't exactly equal 0. So similar things happening here. 0.999, you can see a lot of them happen first. We're going to say it's approximately 1. So this is approximately 1, and then we have to do the z-score, the probability that the z-score is less than 0.10, so 0.5398, 0.5398. 0.4602. So what proportion of women meet that height requirement? 0.4602, or you could say 46.02% of women would meet that height requirement. All right, the next example. The diameters of Douglas fir trees grown at a Christmas tree farm are normally distributed with a mean of 4.7 inches and a standard deviation of 1.4 inches. And then we have several questions. So first, I'm going to write down that X is the diameter of Douglas fir trees in inches. And then I'm going to go ahead and figure out what each of these are saying, just one at a time. If you feel pretty confident that you can use the formula to convert the X variable into a Z variable into a Z-score and calculate the probabilities, feel free to pause the video, do the calculations, and then come back to check your answers. So this one says, what is the probability that a chosen tree will have a diameter that is less than 3.75 inches? So probability that X is less than 3.75. So first we need to find the Z-score so that we can use our standard normal distribution table. So 3.75 minus 4.7 over 1.4. Negative 0.68. So this is equivalent to the probability that Z is less than negative 0.68. And this is less than, that's the left area, and so that matches the table. So all I need to do is look up negative 0.68. Almost see it all the way over here, 0.2483. So the probability that a tree will have a diameter less than 3.75 inches is 0.2483, or you could say 24.83% chance that the tree will have a diameter less than 3.75 inches. What is the likelihood that a chosen tree will have a diameter between 3 and 5 inches? That word likelihood is just another way of saying the probability. So we're going to say the probability that the diameter is between 3 and 5 inches. And so we need to convert those values into Z-scores. So 3 minus 4.7 over 1.4. 5 minus 4.7 over 1.4. negative 1.21, and 0.21. So this is the probability that z is between negative 1.21 and 0.21. And to calculate this, we do the rightmost minus the leftmost, or the upper bound minus the lower bound. So the probability that z is less than 0.21 minus the probability that z is less than negative 1.21. Okay, so 0.21 is 0.5832. Negative 1.21. Negative 1.21 is 0.1131. .4701. Your tree stand will not expand beyond 6 inches. What proportion of trees will not fit your tree stand? So we're finding the probability that the diameter is greater than 6. So we need to find the z-score first. .93. So that's the probability that z is greater than 0.93. And this is asking us to find the area to the right of 0.93, and that's not how the table works. The table finds the area to the left. And so I'm going to have to write the complement, 1 minus the probability that z is less than 0.93. And then there's 0.9. 0.93 is 0.8238. .1762. All right, so 0.1762 is the proportion of trees that would not fit in the tree stand, or we could say 17.62% of trees would not fit in the tree stand. All right, last question. This is kind of a summary question that's very conceptual for our learning up to this point. So it says, would it be unusual to observe a tree with a diameter of 9 inches? There's a few different ways we could answer that, and here it asks us to provide 3 different justifications for your answer. And our 3 justifications are going to feel very similar, but they are technically different. So the first justification that we're going to use is the range rule of thumb. This is the first way that we learned how to mathematically describe what an outlier would be. And so if we want to know if this is unusual, we're asking, is it an outlier? So the range rule of thumb says if you're dealing with a sample statistic, you would say x bar plus or minus 2s, the mean plus or minus 2 standard deviations. Here we're talking about a population parameter, and so we're going to say mu plus or minus 2 sigma. And so when we do that, we will know what range the typical values are for the diameter of the Douglas fir tree. So we're going to say the mean minus 2 times standard deviation and the mean plus 2 times the standard deviation. And so the range of usual values is 1.9 inches to 7.5 inches. Those would be considered the usual values for the diameter of the tree at the farm. And so 9 is unusual. And it would be an outlier based on the range rule of thumb. So that's one way that we learned to talk about typical values, usual values, or what would be unusual. The next way that we talked about how to determine whether values were usual or unusual, or if they were significantly low or high, was using the empirical rule. And we talked about this with z-scores, we talked about this with standard deviations, we drew out the bell curve, and we wrote down the mean, and we wrote down a few standard deviations above and below the mean, but we specifically looked at the value of the z-score, so I'm going to calculate that right here. So 9 minus 4.7 over 1.4. 3.07. And we said that in a similar way to this range rule of thumb, that when we drew that bell curve, that our typical values would be within 2 standard deviations of the mean, like we said here with the range rule of thumb, or we said that their z-scores would not be less than -2 or greater than +2 if they were to be typical values. If they were to be unusually low values, then their z-score would be less than -2. If they were unusually high values, then their z-score would be greater than 2. And so since this z-score is greater than 2, this value is unusually high. We can tell just by looking at the z-score. All right, now we have a third way, and that's what we've kind of learned how to do today a little bit, but we've also kind of talked about this number, and you'll recognize it when I mention it. So now, sorry about that. My phone is ringing. Now we're going to talk about the probability. So if we look at the probability of having a value, a random variable that is 3.75 or a z-score that is 3.07, I'm going to talk about the probability that we have something that high. We're not talking about the left area, we're going to talk about the right area. So we're going to talk about the probability that z is greater than 3.07. because we want to know if this is unusual. So if we look at this probability, we're going to calculate this by finding the complement, 1 minus the probability that z is less than 3.07. And I'm going to grab my table. 3.07 is right here, 0.9989. When we talked about probability, we said the number that was the threshold to determine if a probability was unusual or not was 0.05. Or 5% if we were talking in percentages. So we said if something had less than a 5% chance of happening, or a probability less than 0.05 of happening, then that would be something that was unusually high or unusually low. So 0.0011 is less than 0.05, and so it meets that criteria, that this probability is even more rare than our threshold, and so we would expect this to be an unusually high number for the diameter of a Douglas fir tree at that Christmas tree farm. So all of these different measurements are related. They're related to, having the mean, 2 standard deviations above, 2 standard deviations below, but they're just different ways to say the same thing in a slightly different context.